Sorry, I'm not so concerned about whether or not you got the right answer. I'm more concerned about how you set it up. Did you find the points of limits of integration? Did you draw your picture correctly?
Yeah,
Did you
some
know how to do a disc versus a washer?
Some people didn't get the actual problem itself.
I was busy doing the area.
Yeah.
I just finished the area when you called time.
Yeah.
Really?
Okay, well, you're gonna have to pick up the pace a little bit.
Yeah.
Okay, so today, as I talked about yesterday, we have a new method for finding volumes. And this is something that comes up. If we started with the shell method, it wouldn't be that bad. The problem is, you've now got a bunch of stuff running around in your head. You've got area, you've got volume using discs, you've got volume using washers, and now you're gonna get, and then you have volumes with cross sections. Now you're gonna get volumes using shells. And I'll show you, or I'll talk you through kind of a internal thought process that you can follow that acts like a checklist as to what you're going to do. So what I'd like to see is we get to a point where this becomes a very algorithmic approach. Do you understand what I mean by that? Yeah, do this, do this, do this. Regardless of what happens, answer this question. If it's yes, go here. If it's no, go there. If it's perpendicular, go here. If it's parallel, go there. And then set up your problems. But we have to get exposed to this first. So we're going to talk about the shell method. And then we're going to talk about how to tell when you go from disk to shell, which one you should use. By disk method, I'm incorporating washer into the disk method because the washer is actually just a subset of the disk method. And then you should all be able to, anybody qualified for CPR?
Qualifying small.
Awesome. So if I fall over, you know what to do.
Well, who should perform? Who should perform?
Just sit around in a circle and talk about it until you're comfortable. Nominate someone, vote on it, and then, after 10 or 15 minutes, somebody can step up and do CPR.
Yeah. Oh, yeah.
Okay, so let's go to Sketchpad because this does a nice job of illustrating what's going to happen here. Okay, so here's I over-exaggerated what we're doing here. So I've got a big fat honking representative rectangle, okay? And we're going to revolve that around this dashed line. The first thing you should notice is that my representative rectangle is now parallel to the axis of revolution. That's the primary indicator to tell you which method you should use. If it's parallel to the axis of revolution, you're going to use shells. If it's perpendicular, you're going to use discs or washers because it's the same thing. Okay. So we have to do a little bit of geometry to figure out how this is going to work. But in essence, what happens is it's the same procedure that we used before. We're going to take that puppy and we're going to spin it around the axis of revolution. Okay. When we do that, we get something that looks like that, which is obviously not a disc. It's not a washer either. That thing is called a shell. What is it geometrically? I mean, you never talked about the volume of a shell in geometry. How would you describe that geometrically?
Cylinder without.
Yeah, a cylinder with a hole punched through it, or a cylinder minus a cylinder. Okay. I'm going to show you the derivation of where the shell method comes from because, as you know, I'm not a big fan of memorizing, so I think it's important that you understand where this comes from because it'll help you remember how the formula works. So if you do the whole thing, then you get that shell thing. And again, same thing as we talked about before. If I want it to be prettier, I can make the rectangle skinnier and eventually take it down to 0, which would give us that that thingamajobber. What am I doing? Differential. Yeah, the thingamajobber. I don't want this one. I clicked the wrong thing. Let's quit this and go back to the, don't save, and go back to the slideshow. Okay, so here's the shell thing. And there's a couple, this is fairly confusing, but there's a couple measurements in this picture that we were concerned about. Number one is the height of that thing. The height of the shell is the same as the height of the rectangle. Is that obvious?
Yep.
Okay, good. I got one yep, it's enough for me. There's two radii that I'm concerned about. One is the radius from the center of the shell all the way out to the farthest distance. We called that capital R. Here it's R1. The other one is R2, which is the smallest distance between the axis of revolution and the shell, because this shell has some thickness. Okay, and again, for this purpose, I accentuated the thickness so you can see what you're what you're dealing with here. That distance then, that little guy right there is delta r, the thickness of our rectangle when we spin it. And what would we like delta r to be?
Yeah.
Dx or dy, depending on what shape we're going. And then there's this little r guy in there. And the plain old r in this picture is being defined as the distance from the axis of revolution to the center of the shell. Okay, so you with me here? So now we're going to start, I'll take you through this. You guys are cowards. You told me what this was. This shell is a cylinder minus another cylinder. So the first one here, pi r squared, r1 squared h, is the volume of the whole big cylinder. The second part, pi r2 squared h, is the volume of the hole in the middle. Okay? So are we all right with that setup so far? Okay, good. So then I did some math. I factored out a pi h, because they have that in common. And I'm left with r1 squared minus r2 squared. That's the difference of perfect squares. So I factored it into that. We good? What's this?
Delta
Correct.
R. Yeah, unquoted.
What's r1 plus r2?
R. No.
The diameter minus
Oh, delta R as well.
R1 plus R2 divided by 2 is the average radius, which we're calling R. So I needed, that's why all of a sudden a 2 appeared and a 1/2 appeared. I needed a 1/2 in there for this. I can't just randomly stick in 1/2s, but I can stick in a 2 if I stick in a 1/2. Okay.
Wait,
So we, go
which
ahead.
one's delta R? Like. the-
R1 minus R2 is delta R. This
So it's like the-
R1 plus R2 divided by 2 is going to be R, the average radius. And then we're left with this mess over here. Okay, there's more coming, be patient.
Okay, so delta R is like the thickness of the cylinder.
Delta R is the thickness of, which we're going to turn it into a dx, that's easy. And then R we're going to define in a second. Taylor?
Why are you putting in 2s and 1/2s? Just
Because I want to get an expression for R. As the thickness of the shell decreases down to 0, it becomes a segment. And so I'm not going to theoretically have an R1 and an R2. I'm going to have one value. So I want to turn this thing into one value, which would be the average thickness. As it shrinks from the left and the right, eventually it reaches 1 point. That gives me the 1 point. Okay? We're getting there. Be patient. Okay. So there's what we said. R1 minus R2 becomes the thickness, which we call delta R, or preferably for us, dx, because we want it to be really skinny. Which turns that into this.
Can you go back?
whoa, why is it over there?
Why'd you move it?
Because I usually am over here. I happen to be over there when she has me. Yeah, so that. Just kind of like, you know.
Your plan failed you.
Can you poke it when it's in your hand? Will it
Sure.
still work?
Where does it belt?
Like it's
That would
moved
be
it right
All
now,
right.
would it work?
True confession, I really can't wear it as a.
I'm sure you
Add some tape.
Yeah.
That'd be really cool.
Really, would it?
No. They just started like.
You can also cut them into little pieces and hide them all over the room.
Does
I
it
gotta
only
be
work?
I gotta go there to change to red. I gotta come up here to change.
That would be an awesome prank.
Does it work if you touch it right now in your hand?
That's what I asked.
No, with your finger. That's what
Oh, with no, you need the pen is the magic. My finger.
Right, you can move on. Don't.
Okay, so. All right. After all that rigmarole of difference of perfect squares and R1s and R2s and everything else, we get down to this. That rectangle that we've been working with from day one, that representative rectangle, is now here. The area of the rectangle, which we've done already. Height times thickness, and the thickness is going to be dx or dy, depending on which one we want. And then this is the new thing, distance away from the x-axis. How far is that rectangle away from the x-axis? Sorry, not the x-axis, the axis of revolution, which we represented as r in the picture. Okay, so I introduced as r1 and r2, but then like I said, as it continues to shrink, we just have one value of r. And that r is the distance away from the axis of revolution. Okay. Yes, sir?
Are we gonna have to like ever derive this?
No. But again, I think it's important that you see where it comes from so that these things don't just pop out of nowhere. But I'm not stupid. I realize in 2 minutes you're going to forget it. You guys are like goldfish. Short-term memory. Okay. This is what? Well, it's true. Why would you remember something that, no, I just told him he doesn't need to remember?
I'll remember it.
No, you won't. No, you
Yeah,
won't.
you know, a little bit on your nose there.
Brown.
Good.
Oh,
Yeah, there you go. Good. He didn't get it until you said something.
no, I got it.
No, you didn't.
Okay, so then of course, we integrate that, because once we find one shell, that volume is just going to be a series of shells. So like it says, we use the integral as an accumulator. That x represents the distance away from the axis. That was our r in the shell. What's f of x dx? Area of?
The little shell thingy.
No.
Area of the rectangle.
Area of the rectangle. A to B is simply where are you taking rectangles from. It's like every other limit of integration. The thing that gets confusing is notice shells have 2 pi out in front. Discs and washers have only pi. How are we doing so far?
Why does it? I was gonna ask why does it have 2 pi, but we already did.
Yeah, that's why we went through the derivation. Okay, we're good? All right, here we go. So here's another picture of what's going on, simplified into terms that we got rid of the R1s, R2s, Rs, and all that other business. dx is the thickness of our rectangle. F of x is the height of our rectangle. Therefore, f of x times dx gives us the area of that rectangle. X is the distance that rectangle is away from the axis of revolution. Integrate it from A to B. We're done. Multiply by 2 pi. Got an answer. Everybody's happy.
Did you say f of x is so?
F of x is the height of the rectangle. Right. Okie doke. Let's try it, shall we?
Sure.
Okay.
All right.
All right, all right, all right.
Actually looks good.
Any idea what 6x minus x squared looks like?
No.
Could you guesstimate?
It's like,
Looks like, were you flashing gang symbols, Eric?
yeah. The part of the upside down parabola.
Yeah, it's an upside down parabola in this guy. I think I got a picture of it. Yeah, that's what it looks like. It's an upside down parabola. That's the blue part that has 1 point at 0 and 1 point at 6. Got the whole shell in there for you.
Thanks.
No problem. Realistically speaking, you're not going to draw that shell unless you're feeling really energetic. Knock yourself out. You're going to draw this. Okay, there's my representative rectangle. Its height is f of x, which we know is 6x minus x squared. Its thickness is dx, and we know that it's x units away from the center of the circle. Notice I can put that representative rectangle anywhere. It could be here, 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 here. That distance will still be x. X is going to change when we start revolving around things that aren't the axes. All the pieces that you need are in that picture. Now set up your integral. To be honest, I don't really care if you want to solve it now or where you can fn int it or whatever. I'm more concerned that you can set it up now instead of go through and grind that thing out. All right, we got it. Any problems? Should look like this, like this, like this. All right, we're getting there. Hold on. There it is. You got a 2 pi because it's a shell. We're going from 0 to 6 because we're taking rectangles starting at 0 all the way out to 6. The area of that rectangle is 6x minus x squared times dx. That's the back end of this. And it's x units away from the axis of revolution. Let's pretend you didn't have a calculator. How would you take the antiderivative of that?
Distribute.
Distribute, so we'd have 6x squared minus x cubed. Take the antiderivative of each part. Plug in 6, plug in 0, subtract the 2, multiply by 2 pi, you're done. Okay, so not too bad of an integral to do. And I got, whoa, I thought I had an answer on there. Did I not? No, I didn't take it all the way through. That's not really that fun to do without a calculator because I don't know what 6 to the 4th is. 36 times 36. You see
What's
big
that?
hunky number?
What's that?
Oh, you want me to do it? What am I, performing circus, Jim? I was close. Yeah. Okay? So at this point, I'm more concerned about you getting to this point, setting up the integral. I think you can all, you're all pretty adept at finding integrals now. So let's look at another example. Now we want to put it around a line that's not one of the axes. So we have to take some other things into account. Stay with the same procedure though. It's a shell. Now why is it a shell?
Because it's parallel to the axis of revolution.
Beautiful. Question number 1 you should ask yourself in these problems. Is my representative rectangle parallel to or perpendicular to the axis of revolution? If it's parallel, which this is the case, it's a shell. If it's perpendicular, then you have to ask yourself, is it touching or not touching? Then it decides disc or washer. We've done those already. This is a shell. How far is that rectangle from the axis of revolution? Here's the line. There's the rectangle.
Oh, wait.
Okay, so first of all, how far is this distance? X. Therefore, how big is that distance? 5 minus x. Well done. Right minus left. How tall is that rectangle? X plus 4, or yeah, x plus 4 minus the quantity x squared plus 2.
Wait,
How
are we-
thick is it?
Y equals x squared or y equals x squared plus 2? They're different.
Oh, they are different. The picture's wrong. Let's go with x squared plus 2. So the whole thing would be shifted up. So the rectangle is the top minus the bottom. Its thickness is dx. That gives us the back end of the integral. It's 5 minus x units away from the axis of revolution. You put a 2 pi out in front because it's a shell, and we're integrating from -1 to 2, which gives us that guy. Whoops. Yep, there we go.
Should you have gotten that all from just the equations?
That's my second.
Yeah, I skipped that pretty quickly. Over there in the bottom corner somewhere, there it is. I set the two functions equal and solve for the points of intersection. I actually just read them off the graph, but that's how you get them. This one, not so easy. How do you take the antiderivative of that? Yeah, you pretty much have to distribute that. Well, clean up what's on the right side first. So you'd have negative x squared plus x plus 2.
Oh, it's actually not that.
Then multiply that out by 5 minus x. Then you'll have a bunch of terms, integrate each one, plug in 2, plug in 1. Or fn int it.
How'd you get all those again?
Okay, so reviewing.
Yeah.
This is the distance away from this axis of revolution, right minus left. This is the height of that rectangle, top minus bottom. That's the thickness of the rectangle, base times height. There's a 2 pi out in front because it's a shell, and those are my limits of integration because I'm going from there to there.
You said the x was 4 minus that, that's, you said the height.
This is top minus bottom, right? It's that distance right there in the picture. Yeah.
Where'd the plus 2 come from?
The function was x squared plus, my picture's wrong. The parabola should actually be shifted up. Okay. Just for discussion purposes, when you multiply that puppy out, you get a cubic, and I think from that point on, you'd be okay with that, right? Okay, good. I think I did it. No, I didn't. Another example. Where's my, I screwed up and moved the other side. Okay. Of course, we need to look at what happens when you work with horizontal rectangles spinning around a horizontal axis of revolution. So I have something that looks like this. I've got this weird function 2y cubed minus y to the fourth. You would not be expected to know what that looks like. And because I don't know how to solve that for y, I'm going to do everything in terms of y, solving the function for x, because the function's already solved for x. There's my rectangle. And again, keep this algorithmic. We're revolving around the x-axis. The representative rectangle is parallel to the axis of revolution, so therefore you're going to use a shell. So you got a 2 pi out in front. I'm integrating from where to where?
0 to 2.
0 to 2, starting at the origin, going up to the y value of 2. Good. How far is that rectangle away from the axis of revolution?
Y.
Y. Good. What's the area of that rectangle? How wide is that rectangle?
dy.
dy. And okay, yeah, good. And how
2y cubed minus y.
2y cubed minus y to the fourth. This distance here is 2y cubed minus y to the fourth. It has a thickness of dy. And those are the components you need for the integral, which leads us to, we did that, height, good, yep, and there we go. Okay. So again, think of the shells as being 2 pi times distance away from the axis of revolution times the area of the rectangle.
Will we get if you said we're not expected to know what it looks like, will we get a graph?
Yeah, if you got
That's where we
something
get
ugly
the-
like that, it'd either be a calculator-based problem where you could plug it in and get a picture, or I'd give you a picture of
And
it.
that's how we get the limit of integration.
Yeah, because this would, this function's not bad. You could set it equal to 0, factor out a y cubed. You'll get 0 and 2. So that one's solvable, but if it gets really nasty, I'm not expecting you to solve it. Normally, you can't solve a cubic unless you've got something nice like that that's got a GCF in it. All done. Okay. Like I said, tonight's homework probably shouldn't be that bad because I think you're just doing shells. But as we progress through the rest of the chapter, when you start looking at problems where you're asked to decide what method you want to use, or what's more common is, here's a problem, solve it using shells, and solve it using discs. Here's a question to solve it with washers and with shells. And so you'll start to see, as you practice this more, given the opportunity on how to solve it, almost every time one method is a lot easier than the other. Because you would think, well, I'm just going to learn discs and washers, and that's all I'm going to go with. You'll see problems where you're forced to use shells, but you'll also see problems where the shell method is actually easier than doing discs or washers. Question?
On the AP test, are they going to tell us like which method to use, or is it just kind of?
I've seen everything.
Okay.
Here's a region, revolve it using shells. Here's a region, use it revolving, blah, blah. Here's a region using a vertical rectangle. So if we go back real quick to address your issue, if I just gave you this problem and didn't tell you what method to use, you'll realize that if I try to do a vertical rectangle here, it's going to get ugly. I'm going to have to go from the function itself down to the function. That usually doesn't work out very well. So you're almost forced into doing a horizontal rectangle, which then makes it parallel to the axis of revolution. and it's a little more manageable. Okay? All right, so tomorrow we will we'll go over the cross-section problems.